world is going to end in 35 seconds.
Haven't got much time.
And we've got the opportunity to restart the human population. But to do that, we're obviously going to need a male and a female to do this. So write down the name of a male and a female.
I could just tell you instead.
You can just tell me instead. The tradition is we'll try and make it, famous people, so we can kind of have a laugh and think about this.
Sure.
Okay, so.
All right, male Bert Russell. I think is it Bert Russell? Who's the guy Magnum PR? Is it Bert Russell? I need to look this up. Tom Selleck. Who the is Bert Russell then?
I don't know.
Welcome to the second episode of the Design Podcast, which we're now tentatively calling Toasting Design. The reasons are our own for that one. No one made any other suggestions, so that's on you. Oh, by the way, that's another thing. Rules. Once again, rule 1, no mentioning of design if you ever mention design task. Number 2, swearing. I don't do well with that one. And number 3,
no mentioning of Bert Russell.
And today we're joined by myself, Schekman, Mr. Boer, Mr. Michael Boer, and a new one, Mr. Mangera. You sound very happy about that. And today we're tackling what I've known as the boy-girl problem.
Yes, we're doing the girl-boy problem, or boy-girl problem.
Same thing.
Pink versus blue, etc.
Sure.
And then we're going to be discussing what design projects are at the different years of study to finish that off. So it's a problem which I do with the third years, and it's about in its 10th year running. So I'm just going to hand over to Tahira and Shaka a blue and a pink piece of paper. And the problem is as follows. The world is going to end in 30 seconds. We need to nominate a male and a female to restart the human population. The world ending, all the people are going to be taken out by some quick acting, Donald Trump inspired death cloud, and we need to restart the human population.
You tried to stop a hurricane.
But the world is largely undestroyed. The only caveat to this is that the male and the female needs to be sort of well known, so we can have a bit of a giggle about that. So in no particular order.
Don't say Bert Russell, by the way. I don't know who Bert Russell is. Okay, I'll say as a male, Tom Selleck.
Oh, that's a nice one.
Yeah.
Male. Jeez. Oh, I'll go with, what's the Canadian Prime Minister guy? Justin Trudeau, yeah. Let's go there.
Okay.
Painted up as himself, or?
And then a female, I'll go Keira Knightley.
Any particular reason for that? Yeah. Female. Shucks. Okay, let's go Charlize Theron for giggles.
South African accent, Charlize Theron, though.
Yeah.
Right, so we have got 2 males and 2 females. Right, yeah. So that we should be able to, pick the best combination of this and then restart the sort of human race. With all the people gone, what's the first problem that these 2 lucky folk are going to run into?
Obviously, establishing the world ending is then the world is still there. It's just people have suddenly vanished.
Correct.
That's the world ended, and no nuclear fallout. Trump wasn't that successful.
Correct.
Good stuff.
All 4 of these people normally reside in North
so we got all 4.
No. Well,
okay.
In terms of
in terms of who we have. Yeah.
Okay. Well, okay. Yeah. All right. Power.
Yeah, who runs the power plants?
Yeah.
If nobody's there, how long can they run themselves for? And all of those nuclear ones? Or
Okay. I've watched Chernobyl.
Wind turbines will keep spinning, but unless you maintain a national grid, power is going to last for a certain amount of time, and then that's just going to...
And then that's it, done.
Next problem.
Food?
Yeah, that's top of the list.
No one's turning pigs into bacon. No one's turning wheat into pasta. No one's planting food.
Breeding the cows and
correct.
So on.
No one's milking anything.
Are we assuming that animals are still existing?
Animals still exist, yeah.
It's very convenient.
Yeah.
Okay.
What else in terms of daily issues?
Medical concerns. I mean, your tablets, your
yeah, you'll be able to
everything. They got
things for a while,
and then they got their expiry dates.
Everything expires. Who's going to run the internet? The viruses will take over the world.
Google is done, unfortunately.
Google will die. Yeah.
I'm pretty certain we put this up online. Google's going to target us now. But so you're lying. Yeah, so you want to be near a library, I'd say. Well, I mean,
you probably need to be near a clean water source. So you
well,
have to
I mean,
purify water.
internet's down. You've got no communications. Not that there's anyone to talk to, but
Yes.
if the two people decide to go, on separate expeditions, one water, one food, you can't talk to each other.
Unless you find some walkie-talkies.
Walkie-talkies, but then batteries. Who makes new batteries?
So it's an interesting thing. So what is the first sort of skill set that these people are going to need?
Warmth.
Yeah, fire.
Warmth, clothes, and fire.
And access to clean water.
Yeah.
And clean water. I always
All
forget
right.
about
So
clean water.
in terms of out of these, if obviously there's skills, etc. as well. Anyone know anything about Charlize? What skills does she have? I mean, she grew up in Benoni.
Yeah, you grew up in Benoni, yeah. So I mean, I'm not worried about her. I mean, it depends between Tom Selleck. I don't know what Justin Trudeau did. I mean,
He's the president of Canada.
I get. No, really.
I mean, got a couple of projects that is mentioned. Niagara doesn't run out of water.
And America doesn't invade.
Tom Selleck was in the Marine Corps. I know that much.
Oh, so he's a good
Knows his way
choice.
around a gun and a first aid kit.
How old is? I mean, between the two of them, Tom Selleck is ancient.
Yeah, and other one's opposite.
Yeah. So we're then stuck with a little timeline, all right? So I'm not an expert in these things, but it takes about 9 months for our two to become three.
Give or take, yeah.
But then you're left with a gap in the timeline. So you can keep having
Those,
babies,
yeah.
but those need to, and of course, incest aside, they're going to have to wait until they get to a reasonable age to do this.
Yes.
And doing this without any medical facilities, no working ICUs, no ultrasounds, nothing.
Yeah.
So what skill sets do you need? What checks would you need to do on these two people before they were chosen?
Well, number one, can they produce the
Exactly.
future generation?
Secondly,
Yes.
do they want to?
Yeah.
A, do they want to? And B, do they have any kind of major genetic things? We're building the entire
Yeah.
human race
That's
off of
right.
them.
Yeah.
One's exposed, he gets cancer every 6 months. Probably not the best choice.
No.
That's true. And the other thing is, unless you've got people that actually sort of converse in, say, several different languages, once all these kids that you have get to a certain age, whether they are libraries or not, it's very difficult to learn a language or different cultures.
Without
from
someone
yours.
speaking it, yeah.
Yeah, and there's no electricity, so shit saying, oh, we'll just watch the videos.
No.
That's not going to be an option either.
Correct. So what we're trying to say here is that when it comes to things like you're presented with a problem as an engineer, there are a million different things that you have to do in your head at sort of split second timing, and you have to go through all of this because what you guys were given a very short time to come up with were concepts.
Yeah.
The thing is, you have to really, really think hard before you jump into a concept, and you've got to think. What's the background to this? What do you need to know? And the thing is, that's the skill that's not written in any textbook.
Yeah. It's the problem. Your problem is something that guides you the entire time. If you know what your design problem is, you know what you... Anytime you come to a decision, there are other criteria or considerations that you need to take into account when making a choice. But fundamentally, it's which one of these solves the problem the best.
Yeah.
And if you don't know that problem, you don't know how to solve it. And if you don't define it properly. So if you're talking about trying to choose between these two people or define their skills or what they need to come up with or do as options, as concepts, and you don't know exactly, okay, you're having them build a power plant when reality, Tom's getting old and we need to look at actually how to support him in his old age. Halfway through building the power plant, Tom's dead and now Charlize is all on her own. Yeah.
So it's an interesting one to get the brain.
All right, nice start for the day.
Right, should we dive into design projects for students?
Yeah, design projects. Okay, so what we're going to talk about then
How about what the difference is between an actual project in industry and what you'll do as a day job versus the game which is called university?
I think for me, okay, maybe I'm wrong, but for me, the difference there comes more in the communication thereof. You're all doing fundamentally the same thing. you'll find some people tell you, I don't do this, I don't do a PRS or a URS, I don't do concepts. You do, they do. It's more they're at a stage where, given the number of times they've had to do that particular design or that particular system, it's just the same thing and it's over. So you know what your options are, you know you're going with this one and you're just developing it thereafter. With an undergrad thing, we don't know that you know that. You need to prove to us. In order for us to let you loose in that big wide world and say, yes, go, frolic, don't hurt people, please. You then have to be able to prove to us that you actually are making those choices. You actually are deciding or evaluating your alternatives and analyzing and understanding what you're doing so that we can say, okay, you can now go and pretend that you know what you're doing. At least that's my understanding.
The really cool thing about having a job is you don't have to go and do maths tuts and business management projects and things like that while trying to actually do the fun stuff.
Yeah.
I'm going to start at second year level.
Yeah, sure. What outline of?
So what should second years be able to do as this mythical thing called design? What are we really aiming? Because there's obviously the way that students see it.
Yeah.
Oh, we have to be able to do these tuts. We have to pass that test. We have to pass that project. But those are just the obstacles in the game.
I think at second year we're looking at figuring out what the problem is. So we're still giving you a broad, open-ended thing, and go and figure out what is the actual problem that you're trying to solve. Because I think that's the main thing with any year, but we start at second year, because if you don't get that skill early on, like Shauk said earlier, you're going to end up just jumping straight into concepts and you're not going to know, you're never going to figure out or the skill of investigating what is the actual problem, breaking it down, and then at each step of the way making logical decisions that link back to that problem. Yeah.
Because there's always the answer to the problem that you're running ahead with what you think is the problem to actually fundamentally realize there is no problem.
Yeah.
And if there's no problem, there's no purpose to your design. No one will buy it. No one's going to pay you. It's pointless.
So what was the project proposed to the second years this year?
So this year was we called it a chairlift. Yeah. So the idea was that it has to be portable, which was the whole thing of don't give something that the problem already exists. So, we have stair lifts. They're everywhere. We see them. But the idea was that the portable was the keyword that you had to sort of pick up on and figure out what portable means in terms of your project. So, the idea was that you would define what portability was to you and based on the investigations that you did into the problem. So portable could have been a variety of different things. It wasn't set at all. And depending on how you define that would basically take your whole project forward.
Well, that would define your problem.
Yeah.
Is the problem located to a small sector of buildings on a campus and you're just moving it from building to building, or is it a nationwide thing?
Exactly. Yeah.
Or a student thing. So do the students need to carry it in their backpack? And it's not just a case of saying, I'll choose the student backpack one, that sounds good.
Yeah.
You need to show it's an actual
problem.
Exactly.
Yeah.
I think the thing which we're looking for second years to be able to define is you don't have to use maths to prove it at second year level. You don't have to use maths to prove everything.
No.
You can describe that an elephant is portable.
Yeah.
To a very small degree.
Yeah.
Yeah.
A pocket knife is even more portable than an elephant.
Yes.
But if you're going from A to B with no obstacles in the way, they're both equally portable.
Exactly.
In fact, the elephant can carry the pocket knife, not the other way around.
Yes.
And at second year level, that's what we want them to try and do.
Yeah, because the other thing is then, if you go too big in your problem scope, the project becomes too much.
Yeah.
You're trying to do too much. You're trying to fit the elephant and the pocket knife into your pocket so that the students can then transport it, or the people can transport, or the people that need the chairlift can transport it. When if you just define your problem as actually being portability with, or if you, depending on how you define your portability and who's using it and their strength and so on and so forth, you never consider elephant in the first place.
So if we were to just go back to Tahira for a second, you've obviously started marking the reports, etc. What were the main how did the students break the problem down? Like, what were the major aspects that they looked at?
I think it's a typical thing of take something that we say and then misinterpret it. which gets difficult. So we gave them this additional exercise where we said, go and look at widths and look for examples of widths where a device like this would be useful. So then we ended up with a whole lot of reports that design something specifically for one building, which then obviously ignores the fact of portability at all. Because if you're designing it for one building, why can't it just stay in that building? So that was the biggest hurdle we had. And then we had some good ones that sort of identified maybe Wits campus then is a good place to start. So students here have difficulty in accessing certain buildings, so maybe they just need to carry it around here. That makes it a little bit easier because maybe to be portable, all you have to do is stick some wheels on it and wheel the thing around. Yeah.
How many of them actually kind of identified that whole thing of I'm ignoring portability because of the fact that I'm saying it's only for one building?
There's quite a few.
They've actually identified that they're actually wrong. Or
Identify that wrong? No.
Because that's sort of what we see certainly when we're evaluating it, and we're the ones that are trying to say, or you're trying to prove to us that you know how to do design, so that again we can then send you out, and when your boss tells you do this, you're not blindly just doing that. You're actually understanding what your boss or your client is actually trying to tell you to actually do. We're trying to critique your stuff, not to be harsh and mean, but to see that you actually understand that you know what you're doing. So if you're just saying it's going to be one building, you're saying one building because that then simplifies your calculations and things. Yes. But if deep down you've actually assumed that it will then be able to move from that building and you're making it universal for the other buildings, if you don't say it, we don't know that.
Yeah, if it's not in there, we don't know it.
And we're talking, there is the report.
Yes.
Which is why that is so important.
And again, it comes back to, like you said, communication. So it's literally just the way you say things.
Yep.
I mean, you could have thought it in your head lovely, but if it's not in there, you haven't communicated it.
Yeah.
The way that I'm, ended up trying to help students unpack that problem was that, to me, there were 3 prongs to it. The first was that there was a payload constrained geometry set.
Yes.
And that's a function of who you want to carry and where the stairs are and things like that. The second thing is portability and how closely related they are. And the third thing is, what performance do you want from this thing? But not just up and down a set of stairs, in terms of the portability as well.
Yeah.
And you have to view those 3 things sort of simultaneously.
Yeah.
And the biggest issue that I can see with second years and again with third years when they start is that they think as soon as they've solved that first problem, the problem is then done.
Yes.
And what they don't realize is that your first solution to a problem is just the first solution.
Yeah.
You then have to go and think about everything else and change your mind or throw that completely out and start from scratch.
At times you realize, hopefully sooner rather than later, that the problem you define, you've actually forgotten to take an entire factor into account.
Yeah.
And that problem actually no longer exists. It's whether solved or whatever the case is. So if with it then, once they've then defined the problem, how far are you then expecting them in second year to be able to take that problem? I
mean, from defining the problem, that basically gives you what we call our URS, PRS.
Sure.
So I like the URS/PRS to show that you've defined the problem nicely. And then from that, analysis, I'm not expecting, we say this thing, design, is never ever finished, of course. So I'm not expecting you to go down into every single nut, bolt, weld, screw that goes into this thing. Just the basics of your PRS. Have you shown me that you've thought about those things and how you would analyze them?
It needs to fit into this space.
Yeah.
Show you know how it does that. It needs to go this speed, have this acceleration, carry this weight.
Yeah.
How do you know it can even do that?
That's true. And at second year level, all you have to do is identify the crucial component or set of components, the assembly perhaps, that allows you to achieve that portability or that geometry or that particular performance.
Yeah.
And everything else you leave out.
Yeah.
Exactly.
It can just be in the sketch or defined somewhere, but you don't have to go out of your way to.
No, like I'm not looking for you to analyze the seatbelt connection and whether if this thing jerks, the person's going to fly off at the stage.
Not to say you can then ignore, if you have seatbelts, that you ignore them. You take them into account in your a sizing or weight estimation.
Exactly.
But that little bolt that holds that seatbelt on isn't the thing that suddenly determines the person is now safely reaching the top versus the person is repeatedly bashed against the side of the wall and then finally thrown over the railing. Because I have a feeling some of your designs might actually do that.
Yeah.
And if you were transporting the person up the stairs upside down, obviously
Yes.
seatbelts would be a very crucial
important thing,
component
yeah.
to make sure that you
Not to say that is actually a solution or now a
No.
good reason as to why you need seatbelts.
And there's some that's like, I mean, there's obvious things where if you just, I don't know, take the design, show it to your friend that is not in engineering and be like, how would you feel about sitting on this thing? Because that could easily tell you whether or not this is actually going to be a thing that people want to use.
Yeah.
And I mean, to me, that's a major concern. You can't sell anything if no one wants to use it.
Well, exactly.
No.
Theoretically, if you've defined your problem well enough, and you're not expected to be able to do it 100%
No.
right from the beginning, that's why there are multiple years of study. But ideally, if you define your problem, that shouldn't come about that you suddenly haven't. That no one wants to buy it. If you find you're in that position, you fine-tune your design. You don't have to then completely
Yes.
restart.
Yeah, so if you were sending someone down the stairs backwards, then you'd put a seatbelt on because no one wants to
Yes.
fall off.
Yes.
And also, what I found is that quite a lot of students, even at third and fourth year level, they'll do their analysis of this thing when it's moving halfway down the stairs. But they don't do how does it get onto the first step? Or how
Yes.
does it get off the last step?
Yeah.
And what are the accelerations like? So if you are transporting this person down the stairs, how does, and if it is unassisted and self-propelled, how does that person aim?
Yes.
Yeah.
And was that even, I mean, at secondary level, that could be a one-liner, it could be an annotation on a diagram, and students don't use those sorts of things.
No.
Yeah.
And what I find is a lot of students will draw a sketch, and their sketch is this thing stationary so I can get my loads, because loads are apparently everything.
Yeah.
Because I have to be able to do some calculations from all the other second year courses. And you then sort of point out to the student, but if you just, rotate that weird little wheel thing that you've got by 20 more degrees, there's going to be this horrible little bastard load that's going to really make your life miserable.
Exactly. Just because you've been taught how to do shaft design or free body diagrams on a nice level inclined
Yes.
surface, mg sine theta is not the be all and end all of calculations. You're proving your design works, not that you can do analysis.
No.
That's what other courses are for. That's why you do those. Design is about, right, now you know how to do that. Show us that you can use all these vast tools that you have available to yourself to solve a problem.
And another thing which is quite apparent, building on what free body diagrams are all about, is there were several students that showed an overall free body diagram. So they had this payload with a center of mass, and then they had like contact points on the different stairs, and then they were trying to superimpose all the forces required to move this thing up. And what students need to realize is that there's a reason that you're taught how to break things down in all those analytical courses.
Yeah.
And you also need to understand that analysis, by definition, is breaking something down. It does not mean that you understand it, and it doesn't mean that you can synthesize or build it back up again.
Yeah.
And all you have to do is use the overall thing to work out what the loads on the wheel are, and then the wheel becomes its own little simple problem where you can throw different concepts at that to try and solve it. You can reverse loads, you can move loads, you can play with all sorts of things, and then you can put it back onto the main thing, and then change the main thing, and just keep going.
With that in mind then, what is the difference, assuming you and I lecture, well, Michael and I lecture third year design, what is third year design compared to second year design then?
Well, mine's obvious. Crap that my students' design has to fly.
Okay, well theoretically wheelchair lifts can fly too.
They can fly, yes.
Somewhat overdoing it.
In fact, apparently some of them did.
Yeah, some of them did. Yeah.
This is where you haven't defined the problem, ladies and gentlemen. I mean, technically, yes, it's portable, but in the grander scheme of things.
In the grander scheme of things, it just becomes more complicated.
I think, like, even I sometimes get lost into how to define that. Complicated how? Are we saying, right, now where you... Okay, so the way I see it, let me put it that way rather. When in second year, you might make this assumption you've got this global center of gravity and you've got maybe 3 stages in your design, the sort of opening point, get on the stairs, move up the stairs, and then get off the stairs. A third year design is now taking that further. Now we're expecting, let's look at the it's moving up the stairs, but step per step, or maybe a landing, turning that corner, those extra elements. It's now a moving center of gravity as the person's then moving and repositioning their weight as they're trying to anticipate this corner or the sudden change in slope. Those shifts add an extra element to your design. It's that bringing the design closer to realism. So you got to understand, in second year, my understanding would be that you're not going for that. It's done here, handed to the workshop, they machine it, it's then sent out, and Macro is selling it all of a sudden. You're not getting close to that. You're presenting this is what I think is a good solution.
Yeah, it's almost a concept and proof of concept, sort of.
Yeah.
Basic proof of concept.
Do the first basic checks to prove that it'll work.
Yeah, exactly. Yeah, it's the first meeting with the client to say, right, this is what I want to do, and this, if they've got any questions, but how do you know that's actually going to work? You've got those answers.
Yeah.
And I think more importantly, it's proving that it will work for the most important thing it needs to do. So this needs to be able to go up the step.
Yes.
It might break when it accelerates onto the first step, but once it's moving, it's probably okay. And at second year level, that's more than adequate.
And you're probably also looking at the design on a more global scale, rather than looking at, right, let's see how this tank tread section here, if you have tank treads, it's not the only solution, trust me. How does that then move around that particular radius, and what are the stresses? And okay, let's put a bit of wire mesh in there. You've gone off topic. There are much bigger problems than that.
Yeah.
That's maybe something you might touch in third year, maybe, but maybe even that only in fourth year.
And I think, with third year, it would be a case of including, aerodynamic drag effects. Even though they are small, you are expected to be able to include them in your design. From the, if you've got rotating mechanism, there's air drag in that, and there's air drag on the person, and things like that.
So in theory, once we hand you over to fourth year, and then basically from fourth year, you no longer lecture design. At least in the current state, there are no more lectures. We've given you all you need to know. You're given a couple more courses. This is some more tools and analysis ways that you can develop your ideas further if you need to use them. You don't have to use FEA. You don't have to have CFD in your projects or your designs. But now you're on your own. Now you're given some very rough guidance, but you're defining the problem on your own. You're defining the design from the very get-go all on your own, and now you need to take it further.
So I think what we're trying to say is that all that differs between second, third and fourth year is the level of detail that you need to go in to prove how well the design actually works.
Yeah.
But the actual skill of problem solving, you obviously get practice at second, third and fourth year, but that bit there doesn't get any more difficult, I don't think.
Maybe the only other difference is at second year, sort of, you're told portability is the keyword, whereas at fourth year, you'd just be told chairlift, and you go and figure out what the actual problem is.
Yeah.
That there isn't a portable one.
Exactly. You need to identify that niche in that market or that particular area.
Find the gap.
And then getting back to it, you can't just race ahead. You see so many times that design a chairlift, fine, I found this one online, I'm going to do what they do because I know that works. I can do all my FEA and things like that. And, well, your design does exactly what that one does, except they've got years of experience on you, so theirs is better, it's lighter, it's cheaper, it's all that. Yours is not going to sell. Yours is not. It's failing effectively at what it's supposed to do because you haven't defined what it's supposed to do. You haven't determined if Tom Selleck is the best person to be designing your system, or if it's actually Keira Knightley instead.
If I could throw something strange into the mix, it would be to the students that they might listen to this. They might be part of a group where the group seemed to understand what we were sort of trying to expect, and to them they really struggle to figure out what we're really after. What skills do you think you need to? I mean, everyone's got a certain skill set, but skills are like sport. You have to work on them to get better at them. What skills do you think make a very good sort of, let's use design engineer versus coursework analytical engineer?
For me, it's a lot about envisaging how the system's going to work in reality.
So what are the skills that you need to do that?
Scheiße.
One of them is curiosity.
Yeah.
The number of times I mean, I've got my degree now. I don't need to be doing this necessarily, but I see something cool online or in a textbook. I don't know, that's cool. I want to learn how it works. I want to figure out whether it's taking it apart or actually doing my own little back of the hand calculations to try and figure out why is this better? Why is SpaceX able to land a rocket vertically when NASA is still throwing everything and letting it burn up in the atmosphere, wasting billions of dollars? Why does that suddenly happen? Why did that curiosity, that drive to want to know more, to want to always find the answer, is kind of gets you to that point, or certainly helps.
I think another thing which a lot of our students, well, they've got, but perhaps more in a kind of social environment than in a kind of academic environment, is confidence. A lot of students that come and talk about design, they're not confident. They're afraid.
Doubting their own, they get an answer, but you doubt it.
Yeah.
And I think one of the key design skills is that it's, and we said that last week, it's very difficult to do good kind of problem solving all by yourself.
Yeah.
You have to bounce ideas off other people.
Yeah.
And a lot of students will try and work in their own group, but if you've got 4 similar sort of personalities and you don't have a single curious person in that group, you don't have the kind of loudmouth guy who's fixed lawnmowers since he was 16 or something like that, you then have to bounce your ideas off other people.
Yeah.
And they don't have to be engineers.
No.
Engineers are not the only clever people on earth.
And sometimes the non-engineers come up with the more unique situations because they don't know everything. They're not restricted by this deeper understanding of physics. They propose something that's completely preposterous. It breaks the laws of physics and thermodynamics, but it leads you down actually a different train of thought all of a sudden that you might not have gone down because you hadn't realized it. Whether it's using, they say, just design an Iron Man suit. Like, well, you can't design Iron Man. That's basically perpetual motion. But then you end up with that guy that crossed the English Channel.
On a
hoverboard, effectively. With, all right, I can't create that kind of system, but maybe I can just fly by having something on my feet. And that's that kind of... I'd say then the other one to follow on from that is a general knowledge of what's going on out there.
Yeah.
Keeping up to date with the latest technology so that you don't keep proposing a project material being carbon fiber. It's not the most amazing material out there. Most designs, it's used half the time as fluff, just because people think it looks cool, rather than because it actually is cool. What do you find in terms of second year design that a student comes to you with a problem and you tell them, what about this? And they go, I hadn't thought about that. Is there any kind of particular one that you find comes up quite often?
I don't know. I think, like we said, they tend to focus on payload and loads in general and ignore the rest of the problem. I'd say that's the biggest thing.
Which, in terms of then saying, like, so have you considered this? What is the this they tend to then ignore the most?
It's a difficult one. I guess it always relates back to the problem. It's ignoring a specific aspect of the problem that is, in this case, the chairlift problem. It was the portability.
The other one
so it was fine. I looked at the 95th percentile male, and this is what they weigh, and
which apparently is 67 kilograms.
Which is really low.
Yeah, exactly. I mean, if you actually look at the stats, yes, statistically I think that is the case, but that also takes into account children and the elderly. Yeah. If you actually look at what the average adult male and adult female is, those masses are 10 to 15, which if you're in America, 20 to 30 kilograms higher.
Yeah, and it comes back to that design skills. You need to question everything. Don't just, because I found it on the internet, that is the end of the line, and that's the answer. So I had plenty that were maximum payload 67 kilograms. I don't think I could sit on that thing. So.
Yeah. How many students actually just took their group? They, found, someone had a bathroom scale and said, right, and there's a scale in the lab, by the way.
Yeah.
How much does our group weigh on average?
Yeah.
Because that would be representative of the second year class.
With your safety boots on.
Well, yes.
With your clothes on, let's get everyone stripped down, because in order to get on my chairlift, that's what you now have to do. You have to drop all your textbooks, your computer, your cell phone. You can't take it because this design is at the bare minimum now.
Yeah, it should be student safety boots, ratty copy of Hibbler laptop, etc.
Exactly. Well, that's the other one I find, and it's one I end up having to tell the students the most. Invariably, is just dimensions. You're told you have to fit into a space of 2 meters by 1 meter. How big is that design? It's 2 meters by 1 meter every time. You've got huge empty voids of space because, well, it can be 2 meters by 1 meter. So let's make it 2 meters by 1 meter instead of actually taking into account sizes and how things fit together. And do you want an engine sitting directly between your legs, generating who knows how much heat, vibration, and motion, instead of putting it behind you with a firewall between yourself? That sort of layout, that sort of consideration of size and can't think of the word, presence, is something that I think maybe in part that's just not drawing it. Everything's trying to be kept by words alone instead of actually just drawing out the thing.
That's true. I think there's another word which is key, and that's sort of imagination. And what I find is students will come up with a pretty creative overall concept, and as soon as they've got their loads, they stop thinking about how to be creative with the loads. And if you've got a load and you look at it and think, oh geez, this thing's going to vary in terms of its angle and it's a compressive load, that means I've got to worry about buckling, etc. Why don't you just take that load past whatever you're doing and then just hang a thing from it? That's effectively what bicycle spokes do. As opposed to your traditional wheel, which is a compressive member versus the tensile member. And the students just don't seem to do that. They don't seem to think, I can take this load and I can apply the process and I can problem solve that particular load. How to get rid of it, how to halve it, how to get rid of it using torsion as opposed to compression or something like that.
Putting everything in as a tension compression member means that your loads are significantly lower now. Instead of then trying to think, I've now got this really complex problem where I've got to take into account torsion, buckling, fatigue and things because the shaft that holds my design at the end of this arm is vibrating at the exact frequency of the material. I'm not going to change the material, I'm just going to find out how to analyze it so that I add an extra 30 kilograms on so that it doesn't vibrate itself to pieces. Instead of just, can I get rid of the material? Can I actually just attach it somewhere else or hang it or suspend it via magnetic levitation? That's options. That's still those possibilities. You don't just stop considering. It's certainly when it comes to those things, concepts, your options. It doesn't just I'm starting my design. I have 3 options, 3 concepts. It's never just 3. But let's say you got 3. That's not it. That's not your end of your options. There are options all the way down to the very end of the line to your very last nut and bolt. Am I going M6 or M12? They're all options. They're all concepts. You've got to consider them.
And the concept's never finished. It just gets to a point where it's good enough. There's a reason that the automobile new models get bought out every single time. And there are no real improvements on anything apart from, the modern stuff is improving what's inside the cabin versus, when's the last time, a better wheel bearing was designed for automotive use? And the answer is probably 50 years ago.
And it's cell phones. Look at cell phones. They keep coming out. You have a new one every year or every 6 months in many cases. And fundamentally it was working. You thought, wow, this is the greatest thing ever. In 6 months, wow, this is the greatest thing ever. Well, because that first one, okay, this is good enough, we need to put it out. Right, we've got a bit more time now. Okay, cool, let me add this new camera, or let me put find a way to put a bigger battery in the system. You've got to at some point stop. And that's what deadlines are for. Not for skipping them and moving them to 3 months later so you get that extra time. It's to realize that's how far we're expecting you to go. Just stop at that point and hopefully have something to show us.
Prof. Reed has a very good saying, and that is, how good is good enough?
The students ask the same question a lot. And there's no hard and fast rule. To be honest, there is no... Well, I wouldn't say there's a hard and fast, this is good enough. Because you can't say when you're designing a drawing pin and designing an aircraft, 20 pages of a report, this stress calculation, it means that you can say that is, once you've shown me 5 tables, 5 figures, 2 free body diagrams, and
a pie chart.
And a pie chart and whatever's left over in a piece
to me it's almost how well you sell what you've done. So it's a communication thing yet again. So you almost need to be, another skill is like a salesman. So
swag. You need swag to be a good engineer.
If you can sell that design of that drawing pin, I think that's good enough.
I've had a number of designs in my undergrad career where I put them out, I knew they were wrong. I knew they fundamentally had failed, but you just don't show that part. And look, we're pretty good at picking out when they're wrong. That's what, as lecturers, we've had enough experience now that we can see when you're trying to hide something. But there are times when I'm not talking like a major thing that went wrong with my designs. It was a small thing, but I know I could fix it in this amount of time. I didn't have that time, so I reported as though it was, which if I had to then actually put the design further out there, I just need those 2 weeks.
Or you call it out and say, I know this is wrong. This is what I'd do if I had more time.
Oh, that's the other one, especially actually in undergrad career. That's probably the wiser thing to do rather than taking my particular route with things.
And you'll find that it's much better to actually focus on the kind of problem solving and how you would solve it using sketches and things like that than to dive straight in and present some complex analysis where we can see that you didn't have the correct inputs. You made a lot of random guesses, a lot of them are incorrect. That's actually irresponsible.
Yeah, the whole thing of recommendations for future work, that wonderful section that seems to be the cop-out to everything, where I should have used an electric engine. Instead of the petrol engine that you use throughout the entire design, that is not something that should come about then. It's, while ideally recommendation for future work is more about what's still to come rather than I should have done this. You've got to understand there's certain times where it's not acceptable that I should have done this and I didn't.
Yeah. And I think that picks up on the fact that design is iterative. You thought you were going to use the motor that you were going to use, and then you figure out actually I shouldn't have been using that, and you iterate and you go back, and if that doesn't work, you go on to the next thing.
Exactly. Yeah. You can't be stubborn in design.
No.
You have to accept that things are going to change. As much as you really want to design that double wishbone suspension system, if a good old leaf spring works, you should have designed the good old leaf spring rather.
And that's only if tires were the correct way to
Well,
solve it.
yeah, exactly. That's getting onto the bigger things of, yeah.
Sometimes it's easier to just get a goat than to get a real fancy lawnmower.
Yeah. Or let the grass grow. Do you actually need to cut the grass? Or do you need to iron your clothes?
I knew you were going to go there.
Alright. Well, I think that's it. Okay. Again, so as part of in the link to this video file, if you're watching this on YouTube, is a link to a form where you can give suggestions and questions. Suggestions so that we can improve this if there's any issue you have. And questions for if you want us to answer any questions during the podcast. There was one question posed, but we'll wait till there's a couple more, and then we can maybe do a session where we answer questions, or we'll do a segment where we answer questions to the best of our ability, provided it's a question we actually want to answer. But yeah.
I think we'll be bold. We'll answer anything that's asked. Don't chicken out there, Schekman.
I might have to beep that one out just to save us for the future. But sure, we'll have to pull videos in the future. Okay. Alright, cool. And we'll see you guys the next time. Or you'll listen to us the next time. We'll talk the next time. We're going to talk anyway.